que estaba roncando para que no le viéramos las imágenes que tienen en el correo. ¿Qué? A las 11 arrancamos.
¿Tenés algo ahí o presento?
No sé, ¿cómo?
¿Pero tienes algo ahí?
La presentación
Tengo un seminario viejo que podría dar.
También, los dos, háganle, denle candela.
Es por ejemplo el seminario viejo.
El que diste ahorita, ese que diste ahorita, ese. Sí, hágale.
¿Por ahí cuánto me demoro para saber
Media horita.
a qué discurso?
Media horita, sí. Claro, de una vez ya.
What happens?
Hello.
What happened there?
What happens? We are going to present. Profe. Listo, por ahí conector. Había acá uno, pero por allá atrás. Sí, sí. Es que yo vamos a tocar improvisar un poco. Sí. Listo, pues voy a dar esta misma.
Eso, este tiempo de brillar. ¿De una? ¿Me presento o qué? Ah. Ya voy, ahorita le arreglo eso, mi princesa. Sí, mi amor, sí. Dame 5 minutos, voy al baño un segundo. Profe, venga, siéntese por aquí. Listo. Muy bien, tiempo de brillar, excelente. Alguno que le tome fotos al chico, ¿no? Para eso lo estamos entrenando, ¿no? Claro, eso es de una. Okay, thank you. Well, thank you. Even if we can tell that math is important, yes, and also the language is very important. So you need to be able to communicate your results in English because of first, it is more or less the language in which we all can communicate. So someone from the Netherlands, from Norway, from the US, Colombian people may communicate, and it saves us a lot of travels with simultaneous translation and that stuff, because of somehow the simultaneous translation is not necessarily technical, so we're going to use the technical language here. Thanks for being here again. So as we have 1 hour left for our program, I ask our 2 PhD students to join us and trying to share their current work in data assimilation. So I'm very pleased to introduce Andrés Yarce Botero. Andrés is a former physics engineer from Universidad de AFIT. He also has a master's in applied physics, also from Universidad de AFIT. And he is part of our joint program with TU Delft University and a PhD in mathematical engineering and also applied mathematics. His work has been so far trying to understand and acquire and trying to understand very well what is going on with this data assimilation world. But the problem we are using as the catalyzer or as the main difficult stuff to deal with is our problems in air pollution. So his work is more focused on the emission dispersion of pollutants, and we are trying to tackle the problem of the regional scale on the nitrogen species. So he's going to be able to speak a little bit more about his work, and what he is going to present is part of the training sessions we perform into the program. The mathematical engineering PhD program, it works with the students in different seminars, and what we do is trying to teach them or trying to get prepared for this kind of presentation. So he's going to have like 30 minutes and he will try to get us understand what he's doing so far during his PhD. So thank you, Andres.
Okay, thank you, Lucia. Thank you for everyone to be here in Medellin, for international speakers. This is a presentation that is not supposed to be today, so the idea is to share my recent work, trying to present maybe in a digest way, the way that I understand the data simulation topic. You recently see a rapid draw that I promised yesterday to someone, but to understand all the difficult topics we have working since yesterday, and some of you, if you don't have the mathematical background, sometimes it's difficult to digest. So the important thing is to understand that this data simulation technology is recently used in many areas of the geophysical science, diverse applications. So once we understand the mathematical backgrounds, we can notice how it's going to impact in different scenarios. The data simulation borns in areas of atmospherical simulations, oceanography, and recently we see that is going toward different areas, even finance, medical simulation for diseases, cardiovascular problems, and it's very exciting to see how this mathematical technology is spreading. Today I'm going to talk first from the motivation, how start the research in my PhD. I'm under the supervision of Professor Arnold Hemming to Delft University, and in Medellin, the supervision of Olga Lucia Quintero and Nicolás Pinel. I'm recent in my second year of the PhD. Let's go into this outline. You notice we are in a branch in which we want to make these two worlds get into communication. There is a world of models that were inspired by the nature phenomena, the physics, and we develop equations to describe this. The other side is the worlds of the more related to the hardware, the instrumentation, how to get observations from different sources. Each one of these worlds is not perfect, has errors associated, has an uncertainty that describes this process. So the data simulation wants to get in communication these worlds, trying to improve the results of the models with information that comes in different ways to complement. I like this picture that I modified from the book of Bouquet and Ash in 2016, and it gives you a perspective of how these worlds are related. In the last presentation of Potterhoy, we saw this particle filters implementation and this side of the data simulation when we don't have these Gaussian assumptions and we need to take advantage of another technique. You saw yesterday in the presentation of the Professor Adrián how he explains more in this area, in the variational methods of data simulation. And in the afternoon, we saw the Professor Evensen talking more of this side of the data simulation when we are using ensemble method in which we take different propagation of our model, disturbing some parameters or initial conditions. Recently, with the problems that we have, for example, in the drawbacks, each world have advantages and disadvantages depend of the applications. For example, here we have these in large models, the incapability to have the adjoint formulation of a model takes a lot of time and it's very difficult to implement. Also, if you have a new model version each year, you have to program again these huge matrices of the adjoint representation. So each one of these words recently in the literature, you see that is trying to open the boundary to hybrid formulations in which we combine the benefits of each one of these words, trying to improve. My study area, I'm noticing, is converging to contribute in the 4D environment. I'm going to show some mathematical formulation, but first let's talk more about applications. So when I start studying, maybe because I was more familiar with the instrumentation or physics, not many mathematics. For me, the state space problem was something very abstract. So you always see that the professors try to show you that if you have a representation of a state space, you have a lot of dimension in a vector here, in which we have a model that what it makes is translating the model in a past state to the new time, using here a operator that could be nonlinear or linear, and in each one of these times, one model that maybe I try to draw Colombia here, you understand that there is a subdivision of the space in different grids, depending of if we have kind of model like Eulerian or Lagrangians, which have differences in how this grid is static or not. But let's you understand that the state space is each one of these cubes in which we have some variable of interest. In the Whorf model, for example, in the methodology, we have wind velocities and directions in each one of the grids. In the problems I am interested, we have in each one of these grids is like concentration of pollutants. So in each one of these times, you have the state, the initial state or the past state, could be each one of these variables in each one of these cells. And if you apply a model, you are going to have the next value of these states. So that's the way the model works, trying to propagate in the model, and you have these nice plots of and patterns of some variable. Okay. In the other side, you have the observations, and you also, most of the cases, notice that there is also an operator. In the general way is a nonlinear, this curve H, with also what makes is trying to map from the state space dimension to the observation space. Graphically, to understand this in this draw, trying to think in some masks of sampling. The sense of, for example, I have the Seattle station. IDEAM station. We are here with the IDEAM representation. Here, this is a station. Let's think that we have a balloon here having the measure of in this side. So you have two dimensional in the observation space, not just in two grids. What is going to make this operator is, let's assume we have 100 of these cubes. It's going to map this 100 space state, helping with this mapping operator in order to have in the dimension 2 the value to compare with the model. So that's the graphical thing to understand, because we always start showing data simulation formulation with these two assumptions, model representation and observation. And you notice also that each one of these has some uncertainty associated. And I told you these uncertainties assume Gaussian in the variational and sequential worlds, and non-Gaussian in the particle filters. So it's a way to understand. In the Lotus Euros, what I am doing is using a model. I have a lot of inputs from different meteorological and cover emission, among others, resolve a lot of computational dynamics, and produce maps like this, the concentration of the position of pollutants. The last year we have very nice plots, for example, putting some values of the pollutants in the city. And once you run the model in different times of the year, because this model have as an input meteorological patterns, you can notice where and with what size of impacts pollutants like the NO2 is going to impact. So it's very interesting to think that the cities are also impacting the long distance ecosystem. So all the things we pollute here is going to be emitted, changed with photocatalyst reaction in the air with another contaminant, and gradually being deposited. And when they are deposited, looks, here's like a pattern of the natural protect areas and Páramo ecosystem of Colombia, and we can delimit where is the impact of this deposition. So we can see from the modeling perspective, and you also, you cannot rely on only models, because the models are just representation with uncertainty, but from the model perspective, we can know that there are areas in the northwest that are receiving more pollutants from Medellin, different cities. So that's what I'm trying to do. The basic equation of the chemical transport model relates different operators. Yes, it's a differential equation in which each one of the states in the chemical transport are concentrations. So we have this big vector of millions of states in which we have terms of advection, diffusion processes, entrainment and detrainment, consumption, chemical reactions, deposition, and emissions. So this is the state vector as I draw in the blackboard. Okay, so then we have the expression of a model that is propagating, and we can, from a model, also establish if there are uncertainty in parameters or states. Also, we have a observation operator that translates the word of the state to the observed. We yesterday saw that there, in the variational perspective, what we made is establish a relation between some distances. Could be in two ways: a strongly constrained const functional or a weakly constrained. The difference between both, as yesterday we saw, is when we assume that we are going to take in account if the model has error associated. You can see if this is 0, we have the strongly constrained const functional, in which we are only taking the distance to the background, respect the initial condition, and the distance of the observation and with the model where to compare with the model. Also, remember that you can translate this L2 norm in this another expression. Also, you are not mathematician, you don't understand this step. But don't worry, just take in mind that there are const functions to relate these distances. The problem of the the variational perspective is how we are going to get a minimum argument for this functional that is going to tell us what is the condition to estimate. In this case, and the formulation I'm going to show you is in terms of the initial states. We can also rewrite the const function in terms of parameters, and we have analogous expression. But this is the basic optimization procedure for the const functional. But also yesterday we saw that there is a procedure that allows to have an inner loops in the algorithm that is going to follow you to the minimum of this functional cost in a more wise way. The incremental formulation was proposed by Courtier, and what this makes is telling that we can move the background state that we want to correct, doing just small jumps, just small increments. And okay, if we are going to take this assumption, just having some algebra here, introducing the new functional in terms of this const function, we cancel some terms, and we have the expression in terms of the increment. From here, we made some linearization assumption in order to distribute the observation operator. And you can notice here how appears a linear version of the operator. Just a draw to remember what Professor Adrian told you yesterday. Well, in the difference between the 4D var and the incremental is that we added this internal quadratic approximation in order to try to get the minimum of the const function in a more wise way. These steps added more computational effort, but allows you not to get maybe distract for local minimums. And there are different options of the minimization we saw yesterday in order to make this more efficient. Let's continue with the mathematicals. When we express the first term in terms of the increments, we know something. This is easy for us to calculate the first part. Why? Because we have the model outputs and what we observe. So this is easy. But the big deal is when we have this linearized of the model, linearized based version, this part. What happens here is that in these normal scenarios of models, these numbers are very high. So express these big matrices is a big deal. So the idea here is trying to avoid this step of the adjoint version of the models with going to taking help for the ensemble world. The ensemble world is going to changing the control space in terms of a substitution of the increment in terms of what we don't know what control variable transforms. And we are going to the space of the ensembles. Remember, just to avoid this part because it's very expensive and is the big deal in the variational. Once we make this new control transform change, we rewrite, just putting the change here, and with algebra we have some assumptions here. Maybe we can draw here. For you is, do you understand how this identity comes here, maybe? Or I can continue. Oh, let's continue. Because just you split the L2 norm here with these two terms, and because you have this assumption, the terms cancel, and you have as a covariance an identity matrix here. So it makes it very easy the calculation. But let's go to the nice idea from the ensembles. It's more important in this 4D EnVIVO implementation, which the one that I'm studying. The idea is get information from the fact that we can propagate a lot of time a model, and what we are going to is to approximate the covariance matrix with the expression of the deviation, ensemble deviation. You run an ensemble, different iteration of the model. Each one of the members you can rest with the mean, and that's the way we build a matrix that has information of the members. That's the idea that fit all the methods of the ensemble Kalman filter. But the thing here with the 4D EnVIVO is that we are going to use this idea, but now in the observation space. So this term that I told you that is very difficult to calculate, we are going to replace with the help of the ensembles. So notice here that all these terms you can calculate. This is the value of the observation in each one of the places of the ensemble member, and the value of the observation in the model in the mean of the ensemble. This is the proposition of Liu for the 4D EnVIVO method. Once you have this change, this is just algebra here. You put this y new, and you are going to solve for the new control variable. And once you have this in this new cycle in the 4D EnVIVO, you have to come back. Sorry, here it ends. I put var by mistake, but you come back. Remember the delta x from the beginning, so you find the new delta x, and you start doing the procedure moving in different delta x. Once this new analysis get some criteria of stop, that could be number of iteration, or maybe they reduce the error between the analysis and the true. So that's the thing behind the 4D EnVIVO method. Let's try to see how it works with the well-known Lorentz 96. So this is a very common way to show the performance of a model. Going to a benchmark model that has a very chaotic behavior, and is going to be analogous to the dynamics of the big atmospheric models, for example. The nice thing of the Lorentz is that you can put here as many states as you want, so you can be something analogous to the high non-dimensional states, and you build these expressions. I start changing some parameters to know how the model behaves, and the way that I perturb the initial condition was adding a Gaussian noise to the initial states. And also here we take the spread of the ensemble. This is very useful to implement here is in the inflation tasks that you can perform later if you notice that you have this phenomena of spurious correlation once you are working with ensemble representation. This picture show in one just picture what happened with the 40 state that I model. You have time step, number of states, and in colors you have this measure of how the state is going to perform. You have a synthetic version of the reality, what we know as truth. So the idea is how the background is going to estimate a new initial condition to be more similar to the truth. Doing the assimilation part, you get an analysis, which is the new, what the assimilation algorithm gives you. And this is a way to compare how these two. Maybe if we saw a lot of states, maybe it's difficult to understand what is happening. But let's see only in one, pick one of these states of this picture. Last picture, take one state, and what is happening is this. You have a background in black. The background is the model without assimilation. It's just the model what is given to you. And the truth is the red one. The truth must be what we are going to guide the model to improve. Once we perturb here a lot of initial condition, we have a propagation of the ensemble members. From these ensemble members, we are going to retrieve some information to tell this analysis, which is the assimilated output, where to go. Maybe in this case is not going. Okay, another thing. This procedure is doing in the assimilation windows. So once the model, the procedure going into the window is going to capture information to the truth, and it's going to generate a new initial condition. And maybe in a better case, that was not very good. Why? Because we are taking a very big spread. You will see if we reduce the spread of the ensemble, how it behaves. But just to understand, the next images, what I am doing is telling the model how to get a new initial condition in this window of assimilation. So the model was here in the black. Now he assimilates and generates a new initial condition. When you initialize the model here, notice how the blue is going to follow the truth for one time. This is the forecast time. But here starts again going, because many errors are being accumulated. Just picking some states in another scenario. Another scenario that I modify changing these parameters. For example, if I change number of ensembles, you notice here how when the number of ensembles are getting more, the analysis, the red is going over the other, is improving. So it's very natural, because you have, as you saw yesterday, once the number of ensemble is going more, the error is going to be less and going to have an optimum estimator. If I show, for example, that I'm making more big the window, so the window size is getting bigger. This is not helping us with the assimilation. You can see that the new analysis, this time in blue, is getting worse with the time. So it says that we are accumulating some errors, having this wider window size. If we make another change in the parameters, as for example, the one in the first example, here having the spread in the initial condition bigger, also you notice that with bigger spread is not improving. But, okay, in this case not improving, but as I mentioned, the spread works in another scenarios when you are going to inflate, use inflation in order to reduce problems well known as spurious correlation and filter divergence, for example. Nowadays, I'm trying to move from the 4D envar in the Lorentz to a more complex implementation. To make this, I'm going to show you some early results and still is in work. I made a subdomain of my interest, 0.09 degrees. It could be 9 kilometers in this latitude. I have zones of interest, Medellina's sourcing of pollutants, and initial natural areas of measuring velocity deposition. These both as the parameters that I can impact with uncertainties to perturb the model. Also, I'm perturbing initial condition, so I'm moving to parameter perturbation of initial condition that are states. I want to estimate this both, and also in the future, as you notice, just some. In the first example, I'm perturbing all the domain in an homogeneous way, all the same parameters for each one. But then what I want is to perturbate is in each one of the cells. Because why? Because if I'm going to estimate this condition will be some more realistic in order to generate emission inventories, for example. That is very good. My interest is to know if the data simulation is going to be able to estimate parameters using the satellite information. In the other side, in the side of the observation, what I am measuring in the model, I'm measuring columns. I'm simulating columns. The columns are not more than the addition of the states in the vertical. Yes? This picture is not very relevant, just the addition of the column total for each one of the region of interest. It's easy to know that the region inside this, the continental land have more impacts with concentration of NO2 because it's taking a lot of in the mean of the ocean where it's not very relevant. I'm using observation from satellites, and from satellite very recent active operational, which is the Tropomi, an instrument developed by the Dutch, the Finnish in this company TNO, and it's on board of a Sentinel-5 satellite. This is a very nice picture of NO2, and you can see how the cities gives a lot of measures of concentration of NO2. Maybe this is not very good but to see, but easy to see, but also it's possible to follow the roads of the traffic, the principal roads. And it's something that maybe there is an history of different satellites that have been taking account concentration measurements, the old ones, Yamaki, GOM, and with the time there are satellites with this very nice spatial resolution to see even plumes of contaminants. I start a methodology from inspiration for another works to download regrade and apply kernel convolution to the data in order to have what the model should compare. So these are now the values of the observations for the cities for a week of interest. Each one of these one represent 1 day at 1:30 approximately, which is the time that the satellite crosses over the country. So we have a window of time, one week to assimilate. Notice, for example, that it's very difficult in sometimes to have data. And that's why in Colombia we have a problem, because the high topography makes a lot of periods of cloudiness. So sometimes it's very lucky to find a good week to assimilate, to have a good density of data. As I show you, I'm perturbation parameters of initial condition with this question in mind, how to estimate this nitrogen impact in ecosystems and understand if the satellite data would be useful to be assimilated in order to estimate accurately these parameters. So this is basically what I'm doing, is like building an extra code to feed my model in an inner loop to estimate a better analysis that is going to perform near the observations. So just to finish, because this work is I don't have it's just preliminary results. I'm going to finish with this to take in mind the core of the algorithm. Remember, we are going to avoid the computation of adjoint models having a representation of this quantity with the help of ensemble members, with things that we can calculate. In my case, the Lotus Euros model output, observed in one time and in the ensemble mean. So it's a trick that, from the ensemble perspective of the data simulation, the variational is taking the help to improve. So thank you very much for, if you have questions or suggestions, I'm glad to hear.
Do you have some questions for Andres?
Thank you very much for the great presentation, Andres. So, a general or philosophical question. So, thinking back to yesterday's presentation by Professor Geir Evensen, would it be possible to draw some parallels between 4D EnVAR and the iterated ensemble Kalman smoother?
Actually, it's very good question, in the sense that I had this discussion with Geir, and he made me notice that there is a very near relation. Will be very nice to explore and make comparison of these two methods, and it's something that I'm going to pay more attention. I already have some new reference to study, because well, I don't understand very good where they are difference, because in this moment I understand that actually could be very very similar, that if you are going backward in the ensemble smoother in order to estimate this initial condition and propagates again, is similar when you have this window of time in the 4D var, also estimating from the initial condition. So my work now is understand the smoother, because it's still in the implementation. I think I would make something with the Lorentz, an easy model, understand the AES, then the iterative, and make the comparison would be nice. Also, I was interested yesterday in the sense of I see that these methods come from the reservoir models, and they have also problems with parameter estimation. And I also am estimating parameters in my problem, but because the smoother are very recent, have to check also if they use in the atmospheric chemistry and how they can be in this area. Would be something new to have a new contribution maybe. Okay, thank you.
Yeah.
Did you have a chance to look over some of the work by Elias Nino, where there is another iteration or another level of iterations on top of 4D and var. So after you optimize in one subspace, you change the subspace and optimize again. So basically you go further with the optimization. And I think that would be possibly beneficial for parameter estimation. So you exhaust the optimization in one subspace that you have, and then you change the subspace and optimize again there. But of course, you take with you the information that you gained from optimizing in the first subspace.
Actually don't have the answer, but maybe in the discussion, I have to ask you again. This is related to the dual that you yesterday. No.
So if you think of how an optimization method works, right? You have one direction, you do a line search, so you optimize in a one-dimensional subspace. Then from there, you take another direction, optimize along that. Here you start with a subspace. You optimize in that subspace. So instead of having a one-dimension, the entire subspace, you move to the optimum in the subspace. You take another subspace and you optimize the new subspace and so on. So it's somewhat similar to how searching along different directions would work, except that instead of one direction, you have an entire subspace. And right now you do optimization in the first subspace, but this process can be iterated by generating new subspaces and continue. So that's the paper.
Okay, maybe you can share me this paper to get more the idea and discuss. But you are changing a space of the same dimension in the ensemble always, or is because I don't get this part. But thank you so much.
Excellent.
Thank you.
Do you have more questions?
This question is more about the model than the optimization process. How do you solve the boundary problems when you create interactions? Sometimes in boundaries you create noisy signals or errors. How do you solve maybe with a large mesh or with our springs? How do you solve it?
We are working with a boundary condition that are fixed for a big domain. So we receive a bunch of data so that we came from. So, and we start making these nested domains in order to reduce the mesh size and being more interested in some parts. I don't know too much in the area of chemical transport, but I heard that more in the methodology you have to take a lot of attention how these boundaries are cutting some topography, some characteristic of the terrain, because it's factors to generate sources of error. In the tape of the numerical aspects, this model has some routines to verify if you are in each one of the grid cells calculating without getting some errors, numerical errors. Some current conditions, and they guarantee calculating in each one of the cells a bunch of the same computation. So I have to check if in the chemical transport, because also is feed from the methodology the same consideration of where you cut from the boundary conditions to, because it will be an error that is spread. Also, a suggestion for that also is to make your analysis with a time of model relaxation, or because when you start the model, you can notice where the error starts appearing and it starts to stabilize. One week, some days with the model stabilized from these boundary effects could be a good suggestion, for example.
Do you have more questions for Andres? We start to do science and trying to merge our research lines because of it's very important that Professor Sandu mentioned. We are going to Barranquilla, and Elias Niño is in Barranquilla, so we are trying to merge both approaches from Universidad de AFIT and to Delft and the people from Universidad del Norte, and that's how we start to move towards a new research line. Andres is also working with Santiago Lopez, and Santiago Lopez is working on the ensemble-based methods for data assimilation, and we have some works of John Edinson that will be tackling the problem of uncertainty in meteorological models, and also we're going to merge what we do with the Air Force and with the other different universities starting to achieve a main goal to perform accurate predictions on not only chemical transport model but also risks on the meteorological fields. So thank you very much, Andres. I'm so proud of you. You've been growing a lot, and it's nice to see how you present your work really freely and very happy. So congratulations. Thank you very much. 2 p.m. in Fabricato. Yes. Una. Sí. Okay, so thank you. Let me check, please. Valentina. Hola, ¿dónde? Es que estoy acá.